Hello dear student, good morning to everybody. Today let us see last lecture for miscellaneous exercise. Last two lectures we were discussing miscellaneous exercise. So miscellaneous exercise is nothing but is a total revision. Let us see remaining sums. We know that this type of sum we already seen. How to find a second derivative in case of parametric forms are given to us. So let us see today that this example also, because that means almost revision of that type of sums. So here x is equal to a of cos t plus t sin t. X is a function of t. So to differentiate with respect to t, so dx by dt is equal to d by dt of a of cos t plus t sin t. A outside constant quantity. Now give term by term, differentiation to term by term, d by dt of t sin t. That is equal to a of d by dt of cos t as it is. Apply product rule. T d by dt of sin t plus sin t as it is. D by dt of t. Agree with me? Yes. So that is equal to a of cos some function minus sin some function d by dt of some function plus t as it is sin some function cos some function d by dt of some function plus sin t because d by dt is 1. So that is equal to a of minus sin t plus t cos t plus sin t cancel. What we get? A t cos t. Remember, whenever parametric form is there, the derivative of it with respect to given parameter, that derivative should be not equal to 0. Mention that. That means we need to mention this thing. Now what is y? A of sin t minus t cos t. Sorry. What is y? A sin t. A of sin t minus t cos t. Yes or no? Let me see. Yes. Now once again, differentiate with respect to y. Sorry, differentiate with respect to t. D by dt of a of sin t minus t cos t. Minus t cos t. A outside, once again give derivative to term by term. That is equal to a of d by dt of sin t. Product rule. T as it is d by dt of cos t. Why here minus n? Because minus n outside is there. So d by dt of t. Agree with me? Yes. So dear friend, that is equal to what happens? See, d by dt of sin some function as it is cos some function d by dt of some function minus t minus sin t d by dt of t. Yes or no? Cos some function sin some function d by dt of some function. Here cos t. So what we get here? A of cos t plus t sin t minus cos t. That get cancelled. A t sin t. That is our dy by dt. What is dy by dx? And therefore dy by dx is nothing but dy by dt upon dx by dt. What is dy by dt? at sin t. And what is dx by dt? at cos t. Let me see. dx by dt. Yes, dx by dt is at cos t. So what we get? That is equal to 10 t. 80 cancel. So what we get? dy by dx is equal to 10 t. Up to this stage that we know from the derivative parametric form. And same time only also discussed the second derivative at that time also. So we want second derivative with respect to x. So d by dx of dy by dx, that is equal to d by dx of 10t. So what we get here? d2y by dx square, 10 sum function, sec square sum function, d by dx of sum function, t. So can I write the sec square t over dx by dt? Yes. Sec square t. What is dx by dt? That we know. at cos t. So what we get? 1 by at sec t. This is the second derivative. Yeah. So whenever parametric forms are given to us, then also we can find second derivative. As far as x is concerned, in textbook they are giving only one sum. Not more practice are given therefore. And for more practice, I already submitted one assignment to all of you. If you are clear about that assignment, that means each and every problem is solvable by you of that assignment, then there is no problem. Differentiation is very easy. One important thing for differentiation, if you go through all exercise textual as well as through that assignment, see, beauty of differentiation is that there is no need to revise at any time. Only you have to see the standard form. Then you are able to do whatever may be some aspect of one derivative. Okay? Let me see next slide. See here. Yes. What they are asking? Now see, remaining few examples are there. They all are most IMP examples. So let us see. If f of x is equal to mod x cube, so that f double dash exists for all real x infinity. Clear? So, how to find that derivative? First of all, see here. Can I write? Here f of x is equal to mod x cube is equal to, can I write? X cube, x greater than 0, 0, x less than 0, minus x cube, x less than 0. Yes, here it is equal to 0. That we know from the definition of modulus. Now see here. For x greater than 0, f of x is equal to x cube. And we know that what is its derivative? 3x square. Okay? And x less than 0. And for x less than 0, f of x is equal to minus x cube. Implies f plus x is equal to minus 3x square. Of course, f(x) is equal to 0 and x is equal to 0. But see, here we can use the standard forms of differentiation only when that define on some open interval. Otherwise, what we need to, if we want to check the differentiability at a particular given point, then we need to use its definition. So now we are going to show that f is differentiable at x is equal to 0. See how? We know that f dash x is equal to limit t tends to x, f of t minus f of x over t minus x. This implies what is f dash 0? Limit t tends to 0, f of t minus f of 0 over t minus 0. That is equal to limit t tends to 0. Here mod t cube minus f of 0 is 0 over t minus 0. That is t. So that comes out limit t tends to 0 mod t cube. Mod t cube upon t. Say that number 1. If this limit exists, then f dash 0 exists. If this limit not exists, then f dash 0 not exist. Yes. So let us see how to write it now. Limit t tends to 0 plus mod t cube upon t is equal to limit t tends to 0 plus t cube upon t. Why? Because t tends to 0 plus implies t greater than 0. If x greater than 0, then what is fx? X greater than 0, then fx is x cube. X less than 0, then minus x cube. So that is equal to what? Limit t tends to 0 plus t square, and that is 0. Also, limit t tends to 0 minus mod t cube upon t is equal to limit t tends to 0 minus t cube upon t. Why? Because t tends to 0 minus implies t less than 0. And if x less than 0, then fx is equal to minus x cube. So minus sign outside, limit t tends to 0 minus t square, and that is also 0. So both limit exist, and both are 0. Limit t tends to 0 plus mod t cube upon t is equal to limit t tends to 0 minus mod t cube upon t is equal to 0. And therefore this limit is 0. Mod t cube upon t is equal to 0. And therefore by 1 f dash 0 is equal to 0. And therefore f is differentiable at x is equal to 0. And f dash 0 is 0. So we can write f dash x is equal to 3x square. X greater than 0. 0. X equal to 0. Minus 3x square. X less than 0. Okay? Yes. What we want? We don't want f dash x. So that f double dash exists and find it. Now same process we have to repeat for f dash x. Here. Now for x greater than 0, f dash x is equal to 3x square. This implies f double dash x is equal to 6x. And for x less than 0, f dash x is equal to f dash x is equal to minus 3x square. This implies f double dash x is equal to minus 6x. Why? 3x, the derivative of x square is 2x. Now we have to take it 0. Now see. F dash 0 is limit t tends to 0, f of t minus f of 0 upon t minus 0. Can you guess what will be f double dash 0? F double dash 0 is equal to limit t tends to 0, f dash t minus f dash 0 upon t minus 0. That is f double dash 0. Now, f double dash 0 is equal to limit t tends to 0, f dash t minus f dash 0 upon t minus 0. Limit t tends to 0, f dash t upon 0. Why? See, we know that f dash x is equal to 0 whenever x is equal to 0. So what we get? That is equal to limit t tends to 0 f dash t over t. Okay? Say this is number 2. Now this limit, once again we need to find left and right hand limit. F dash t over t. Limit t tends to 0, 50 square over t. Why? T tends to 0 plus implies t greater than 0. And see, we know that f dash x is equal to 3x square when x greater than 0, equal to minus 3x square x less than 0. So that is equal to what we get? 3 times limit t tends to 0 plus t. That is 0. Also, limit t tends to 0 minus f dash t over t. Limit t tends to 0 minus, yes, that we know, minus 3t square over t. Why? Because t tends to 0 minus m plus t less than 0. So that is equal to what happens? Minus 3 times limit t tends to 0 minus t, that is also 0. So what we get? And therefore limit t tends to 0 plus f dash t over t is equal to limit t tends to 0 minus f dash t over t is equal to 0. And therefore limit t tends to 0 f dash t by t is equal to 0. And therefore by 2 f double x is equal to 0. So what we can write? And therefore f dash x is differentiable at x is equal to 0 and f double dash is equal to 0. So what we can write? And therefore f double dash x is equal to, let us see, when x greater than 0, then f double dash x 6x, x less than 0, then f double dash x minus 6x. And at 0, it is 0. So here we can write 6x whenever x greater than 0, 0 whenever x is equal to 0, minus 6x, x less than 0. So from this one, can I write f double dash x is equal to 6 modulus x? Yes. 6 modulus of x. Clear? That we want to find. See, find f double dash x. What is f double dash x? See what they want. So that f double dash exists for all real x, and find it. First of all, x using modulus, then check for the first derivative, then you get the first derivative of this form, then you check for second derivative is also possible, writing second derivative in this form, so it is in form of modulus. Next, see, using mathematical induction, by principle of mathematical induction, prove that this way. We know that what is principle of mathematical induction? For some natural number n, p of n is some mathematical statement. First of all, prove that it is true for n is equal to 1. Except that it is true for n is equal to k. That means first of all, prove that p of 1 is true. Suppose p of k is true. And prove that p of k plus 1 is true. This is the principle of mathematical induction. PMI. So first of all, what we will do? Say given statement as a p of n. d by dx of x raised to n is equal to nx raised to Now prove it by mathematical induction. So for n is equal to 1, what happens? d by dx of x raised to 1. This can be written as dx by dx, that is equal to 1. This can be written as 1 into x raised to 1 minus 1. Yes, we can write it. Because that is 0, that comes out 1. And therefore, what we proved? d by dx of x raised to 1 is equal to 1 into x raised to 1 minus 1. And therefore, p of 1 is true. Yeah. Now, suppose it is true for n is equal to k. That means, suppose p of k is true. Suppose p of k is true. For k belongs to n. So what we get? d by dx of x raised to k is equal to k times x raised to k minus 1. We call this as number 1. Now prove that it is true for n is equal to k plus 1. For n is equal to k plus 1, what is left hand side? d by dx of x raised to k plus 1. Can I write that is equal to d by dx of x raised to k into x? Yes. Now apply product rule. X raised to k is d by dx of x. X is k d by dx of x raised to k. That comes out x raised to k. X is by 1 k into x raised to k minus 1. And this is due to 1. So x raised to k plus k into x raised to 1 plus k minus 1. Base same indices are added. So what we get? X raised to k plus k into x raised to k. That is k plus 1 into x raised to k. Can I write it? Yes. Can I arrange it this way? K plus 1 x raised to k plus 1 minus 1. Yes. So that is the word right hand side. And therefore p of k is p of k plus 1. And therefore p of k is true, imply p of k plus 1 is true. And therefore by principle of mathematical induction, p of n is true for n belongs to n. So that thing we want to prove. And we can write it also. And therefore d by dx of x raised to n is equal to n x raised to n minus 1 belongs to n. Clear? So we can prove this result with the help of principle of mathematical induction also. See, using mathematical induction, prove that d by dx of x raised to n is equal to n x raised to n minus 1 for all positive integer n. That means for all natural. Let us see next one. Yeah, see. Using one standard form of trigonometric function and using derivative, we can obtain other one. What they are asking, see. Use the fact that sin a plus b, that means using formula of sin a plus b and the differentiation, obtain the sum formula for cosine. Same way you can use the difference formula of sine and differentiation, you can obtain difference formula for cos also. That means using formula of sin a plus b and differentiation, we can obtain formula of cos a plus b. Same way, using formula of sin a minus b and differentiation, we can obtain formula of cos a minus b. Vice versa also possible. Using formula of cos a plus b and differentiation, we can obtain formula of sin a plus b. Using formula of cos a minus b and differentiation, we can obtain formula of sin a minus b also. Okay? So, how to do this type of sum? So, we don't know what is a and b. Suppose that both are function of x. Suppose a is a function of x In B is also some function of x. You can take any variable. You can write in t also. You can write theta also. You can write y also. See, if I take a and b both are a function of x, then we need to differentiate with respect to x. If I write both are a function of t, then we need to differentiate with respect to t. Now, sin of a plus b, what is formula? Sin a cos b plus cos a sin b. That we know. Now use the differentiation with respect to x. Differentiate with respect to x, because I am taking a and b as a function of a. So taking d by dx on both sides. Sin a cos b plus cos a sin b. So left hand side I am taking as it is. D by dx of sin a plus b. On right hand side, give differences into both term. Sin a cos b plus d by dx of cos a sin b. Once again, left hand side as it is. D by dx of sin a plus b is equal to apply product rule. Sin a d by dx of cos b plus cos b d by dx of sin a plus cos a as it is d by dx of sin b as it is d by dx of cos a. Yes or no? Yes. Now, sin some function, cos some function, d by dx of some function. Sin a is cos some function minus sin some function, d by dx of some function, plus cos b as it is d by dx of sin function, sin some function, cos some function, d by dx of some function, plus this cos a d by dx of sin function, cos some function, d by dx of some function, sin b as it is cos some function minus sin some function, d by dx of some function. Agree? Yes. Now see. Can I write therefore cos a plus b into bracket dA by dx plus dB by dx? Yes. Now see. See the forms. Cos a cos b dA by dx minus sin a sin b dA by dx. So put it in cos a cos b minus sin a sin b dA by dx. Same thing for sin also. See, minus sin a sin b dB by dx. Cos a cos b dB by dx. So, cos a cos b minus sin a sin b dB by dx. Now you can see that cos a cos b sin a sin b common. So take it common. So what we get here? Cos a plus b dA by dx plus dB by dx is equal to right hand side. Cos a cos b minus sin a sin b. If I take it common. Then what we get? Here dA by dx. Here dB by dx. dA by dx and dB by dx. Now on both sides dA by dx plus dB by dx cancel. What we get? Cos of A plus B is equal to cos A cos B minus sin A sin B. So you can use any form and you can obtain any other one. See? So using formula of sin A plus B, obtain formula cosine. First of all, suppose both are function of x, so we can differentiate with respect to x on both sides using term by term, using product rule, and using a whole standard form. All each and every step is written here. Then you get this one. On same line, you can do for remaining forms also. Let us only these are forms also not there. We can differentiate sin 3 theta formula. Using formula of sin 3 theta and differentiation, obtain formula of cos 3 theta. That is also possible. Let us do that some extras now. Using formula of sin 3 theta and differentiation, obtain formula of cos 3 theta. That is also possible. Using formula of sin 2 theta, you can obtain formula of cos 2 theta also. Using formula of cos 2 theta, you can obtain formula of sin 2 theta also. Like that. So, what is formula of sin 3 theta? 3 sin theta minus 4 sin 2 theta. I hope that all of you have known this formula. Now see, differentiate with respect to theta on both sides. d by d theta sin 3 theta, d by d theta 3 sin theta minus 4 sin cube theta, 3 outside, d by d theta sin theta minus 4 outside, d by d theta sin theta, that we know. Left hand side as it is, d by d theta of sin theta. What is the formula of sin some function? Cos some function, d by d theta of some function, 3 sin some function, cos some function, d by d theta of some function, minus 4 as it is some function cube, 3 times some function square d by d theta of some function. What is the derivative of 3 theta? Is 3 cos 3 theta is equal to 3 cos theta minus 12 sin square theta sin some function cos some function d theta by d theta of some function. Now 3 cancel on both sides. So what we get here? Cos 3 theta is equal to cos theta minus 4 sin square theta is equal to, can I write 1 minus cos square theta? Yes, into cos theta. So what we get here? Cos theta minus 4 cos theta plus 4 cos cube theta. So can I write here? 4 cos cube theta minus 3 cos theta, and therefore you can see that this is the formula of cos 3 theta. So using differentiation and some trigonometric standard form, we can obtain other one. Okay? Yes. Next one. Yes. Most important example. Does there exist a function which is continuous everywhere, but not differentiable at exactly 2 points? Justify your answer. Most timely example, and is a 4 marks example. Suppose that function Remember this function. Mug up this function. 1 x less than 1 x 1 less than or equal to x less than or equal to 2 x greater than. Only remember mug up this function for particular this example. Clear? Now see. Is continuous everywhere. That means we need to prove that this function is continuous everywhere. See, for x greater than 1, fx is equal to, sorry, x less than 1. For x less than 1, fx is equal to 1. And for x greater than 2, fx is equal to 2. Are what? Constant functions. And they are continuous. They are continuous. You know that every constant function is continuous. Every polynomial function is also continuous. Also, for 1 less than x less than 2, f of x is x and is linear polynomial. And it's continuous, that we know. Okay? So, x less than 1, x greater than 2, then both are constant functions, so it is continuous. On open interval it is x. It's a linear function, that is also continuous. Now we have to check the continuity at one end, particular point. And at particular point we want to discuss the continuity. They are given in inequality form. So we need to use delta limit and right hand. How to prove that? See, it is continuous at x is equal to 1. Let me see here. Limit x tends to 1 plus fx is equal to limit x tends to 1 plus x greater than 0 plus imply x greater than 0. And x greater than, 1. Sorry, 1. Because x tends to 1 plus implies x greater than 1. Then it is x, see? X greater than 1, that is x. And that is 1. And limit x tends to 1 minus fx is equal to limit x tends to 1 minus 1, that is 1. Why it is 1? Because x tends to 1 minus implies x less than 1. And x less than 1, that is 1. So, that is 1. And what is the f of 1? That is also 1. 1. X greater than or equal to 1, then x. So, what we see? And therefore, limit x tends to 1 plus fx is equal to limit x tends to 1 minus fx is equal to f of 1. And therefore this limit is 1. Which one? Limit x tends to 1 f of x is equal to f of 1. And therefore f is continuous at x is equal to 1. Okay. So it is continuous at x is equal to 1. On same line prove that it is continuous at x is equal to 2. Then it is continuous everywhere. So let me see. For 2 greater than 2, then 2, otherwise x. Okay. Limit x tends to 2 plus fx is equal to limit x tends to 2 plus x. Why? Because x tends to 2 plus implies See. Same way, x greater than 1, that is also x. And same way, x less than 2. Sorry, x greater than 2, then 2. Sorry. Here it is 2. And that is, now it is less. Limit x tends to 2 minus fx is equal to limit x tends to 2 minus x tends to 2 minus implies x less than 2, then it is x. Yeah? And that is also 2. And f of 2 is also 2. Because x less than or equal to 2. See? Less than or equal to 2 then x. So what do we say? Limit x tends to 2 plus fx is same as limit x tends to 2 minus fx same as f of 2. And therefore limit is 2. Limit x tends to 2, f of x is f of 2. And therefore f is continuous at x is equal to 2. Hence, f is continuous everywhere. And that thing we want to see. See it. Thus, there exists a function which is continuous everywhere. And it is not differentiable exactly at 2 points. Now, say fx is this one. Now, f of x is equal to 1, x less than 1, x 1 less than or equal to x less than or equal to 2, 2, x greater than 2. This implies f dash x less than 1, that is 0, constant function. Function is always differentiable on open interval. So that is 1, for 1 less than x less than 2, 0, x greater than 2. Yeah. So, here we have to talk the differentiability at 1 and 2 only. Other than 1 and 2 it is differentiable. Now prove that this function is not differentiable at 1 as well as 2. Now what is f dash 1? See. F dash 1 is equal to that we know. Limit t tends to 1, f of t minus f of 1 over t minus 1. So limit t tends to 1, f of t. What is f of 1? Over t minus 1. See. F of x is equal to 1 whenever x is equal to 1. So that is nothing but 1. So that is nothing but 1. Prove that this limit not exists. So function is not differentiable. That x is equal to 1. Now, limit t tends to 1 plus f of t minus 1 upon t minus 1. Limit t tends to 1 plus, that is t minus 1, t minus 1. Why? Because t tends to 1 plus implies t greater than 1. If x greater than 1, then what happens? X greater than 1, then 1. X. Yeah? Yes. So that is equal to limit t tends to 1 plus 1, and that is 1. Also, what is left limit? F of t minus 1 upon t minus 1. Limit t tends to 1 minus. Put the result. T tends to 1 minus implies t less than 1. T less than 1, then 1. So 1 minus 1 over 1, left element is 0. Therefore, we can write, and therefore, limit t tends to 1 plus f of t minus 1 upon t minus 1 is not equal to limit t tends to 1 minus f of t minus 1 upon t minus 1. So limit not exists, and therefore this limit not exists. F of t minus 1 upon t minus 1 does not exist, and therefore by 1, if this one does not exist, and therefore f is not differentiable at x is equal to 1. On same line, we have to see that f is not differentiable at x is equal to 2 also. So let us start with f dash 2. Also, f dash 2 is equal to limit t tends to 2 f of t minus f of 2 upon t minus 2. Limit t tends to 2 f of t minus t minus 2. Let us see what is f of 2. See here. See. X less than or equal to 2, then it is x. So f of 2 is 2. So we have to write here 2. Cell is at number 2. Now on the same line, prove that this limit not exists. So check left hand existence of left element and right element. Let me see. Limit t tends to 2 plus f of t minus 2 upon t minus 2. Limit t tends to 2 plus, that is 2 minus 2 upon t minus 2. Why? Because t tends to 2 plus 2 plus t greater than 2. If t greater than 2, then what happens? T greater than 2, then 2. Less than 2, then x. So that is equal to limit t tends to 2 plus 0 is equal to 0, and limit t tends to 2 minus f of t minus 2 upon t minus 2 is equal to limit t tends to 2 minus t minus 2 over t minus 2. Why? T tends to 2 minus plus t is less than 2. And we know that f(x) is equal to x whenever 1 less than or equal to x less than or equal to 2. So that comes out 1. That is equal to limit t tends to 2 minus 1 is equal to 1. Observe that. Right hand limit is 0, left hand 0, limit is 1. So the limit not exists, both are not equal. And therefore, limit t tends to 2 plus f of t minus 2 upon t minus 2 is not equal to limit t tends to minus f of t minus 2 upon t minus 2. And therefore, limit does not exist. T tends to 2 minus f of t minus 2 upon t minus 2 does not exist. And therefore, by 2. And therefore, by 2. F dash 2 does not exist. And therefore, f is not differentiable at x is equal to 2. So what we see? And therefore, hence f is not differentiable exactly at 2 points x is equal to 1 and x is equal to 2. So that thing we want to see. See, once again, let us see, it is step by step. See, n is of 4 marks. Does there exist a function which is continuous everywhere? Yes, there exists such a function. But not differentiable at exactly 2 points. Yes, of course, that is also things is that. So please mug up this standard. Keep this forms in your mind to answer this question. So please mug up, especially for this example. So now see, for x less than 1 and x greater than 2 it is constant function, so it is continuous. And for 1 to 2 opening from 1 to 2 it is linear form, so it is also continuous. Now we have to talk at the end points. That means we have to see the continuity at x is equal to 1 and at x is equal to 2. See here for 1, right hand limit is 1, left hand limit is 1, f of 1 is 1, so all are equal, so it is continuous at x is equal to 1. Same way, it is continuous at 2 also, f is continuous at 2 as well as continuous at 1. And previously you already seen that in 2 cases it is constant function, so it is continuous, and one of the part it is linear, so it is continuous. So we can mention this line, hence f is continuous everywhere. Then we have to talk the differentiability. Fx is equal to this one, gives f plus x is equal to this one. Here closed interval is there, here I am taking open interval because function is differentiable on open interval. That means other than 1 and 2 it is differentiable, that we know. Now we have to check the differentiability at 1 and 2. So at 1, this formula. See, here we can write this is nothing but calculation. See, the right hand limit and left hand limit exist, but they are not equal. So limit not exists, therefore a place will not exist, and therefore f is not differentiable. Same way it is not differentiable at 2. Other than 1 and 2 it is differentiable, hence f is not differentiable exactly at 2 points, x is equal to 1 and x is equal to 2. Okay? Next, very simple forms is there. Okay, what is given? Y is given in determinant form. First row is a variable form. Second and third row are constant. Then prove that derivative is this one. Very simple thing. Y is nothing but fx, gx, hx, ln, a, b, c. Expand it. What do we get? Fx into Cm minus Bn into f of x. Yes or no? Yes, minus sign. Cl minus An. Cl, LC over Cl minus An into Gx plus Lb plus Lb minus An into x. This is our y. Now what do we do? Nothing. Just differentiate with respect to x. And therefore dy by dx is equal to d by dx of all this bracket. Cm minus Bn into fx minus Cl minus An into Gx plus Lb minus Am into Hx. Yes or no? Yes. So what we get? And therefore dy by dx is equal to, this one is constant term, Cm minus Bn, d by dx of fx is nothing but f plus x, minus Cl minus An into d by dx of gx is nothing but g plus x, plus Lb minus Am into d by dx of hx means nothing but h plus x. Now is nothing but the determinant. See, that is determinant f dash x, g dash x, h dash x, L, M, N, A, B, C. See that? Cm minus Bn into f dash x minus sign. Cl minus An into g dash x plus h dash x into Lb minus N. Very simple form. So here function is given in terms of determinant. If first and second row are constant, then what will you do? First of all, expand it in this one. Now in case of MCQ, you can use this standard form directly also. See? Yes. Now next one. See here. What is given? Once again, is a question in terms of cos inverse, that is in inverse form. This y is given to us, prove that this thing. So here y is equal to e raised to a cos inverse x, and mod x is less than or equal to 1. You can write this one in this form also. Now what we will do? Just differentiate with respect to x on both sides. And therefore dy by dx is equal to d by dx of e raised to a cos inverse x. E raised to some form, e raised to some function, d by dx of some function. A is constant outside, this one is nothing but our y. D by dx of cos some function minus 1 upon under root 1 minus some function square, d by dx of some function. So what we proved? Therefore, seeing that dy by dx is equal to minus ay under root 1 minus x square. We've already seen that. After differentiating first term, if possible, then award division. Either to award division rule we can use logarithmic function, or we can use our ordinary simple algebra of mathematics. Take denominator quantity on left hand side. Clear? Now, whenever right hand side consists only single term or single function, then if we square it, then differentiating, then it is very easy to us. So let us take square on both sides. So what we get? 1 minus x square into dy by dx whole square is equal to a square y square. Yes. Now we can differentiate it. And therefore d by dx of 1 minus x square. Can I write here by 1 square? Yes. A square by square. So, and therefore, can I write here 1 minus x square as it is d by dx of second function as it is d by dx of first function. Here also we will write d by dx. D by dx of a square y square is equal to a square common d by dx of y square. So what we get here? 1 minus x square something square 2 times something d by dx of something. By 1 square derivative is 0. 2 times something d by dx of something is equal to a square. 2 times something d by dx of something. Okay. So what we get here? 1 minus x square 2 y1 y2. Here what we get? Minus 2x y1 square. That is equal to 2a square y1. Now divide by 2 y1 not equal to 0. by 2y1 not equal to 0. What we get here? 1 minus x square y2 minus xy1 is equal to x square y. So write in our order, whatever we want. 1 minus x square d2y by dx square minus x dy by dx minus a square y is equal to 0. That we know. See? And that thing we want to do here. See? Okay? Dear friends, this is the end of exercise. See, miscellaneous exercise also completed. In next 2 lectures, we are going to see how to answer the multiple choice questions based on differentiation. Not 2 lectures, almost 1 lecture. Now see, we already seen some extra examples also. What is the beauty of differentiation? Beauty of differentiation is that if you go through all exercise from textbook as well as for all assignments that already submitted to all of you, if you go through these 2 ways, then lifetime there is no need to revise the differentiation. In examination, as far as calculus is concerned, they can ask any questions based on calculus, other than textbook also. No problem. If all forms are clear to all of you, then there is no problem. So dear friends, do these things in 2 ways. Before your exam, that means before your test, please completely revise all the exercise including illustrations as well as all assignments. And if you have doubt, then you can ask me. I am ready to answer all. Okay? Thank you, dear friends.